Okay, let us recall that in the last class we discussed about AC magnetization. That means whenever a core is excited by an alternating voltage source and which in turn results in a flux in the core in such a pattern as to create an induced voltage E which will oppose the applied voltage. Okay. So you will have a flux which is set up in the core in such a pattern to oppose the applied voltage. That means you know that the RMS value of the induced voltage is given by 4.44 into frequency into number of turns into the maximum flux in the core. Now how will that maximum flux come? We have seen that that maximum flux it will come from a current drawn from the source, because the flux that is in the core will be decided by the current, and that current that is drawn we call it as a magnetizing current. That magnetizing current will be in phase with the flux, because you know the flux is the result of the current. So now we have a magnetizing current and a magnetizing which will create that flux, which in turn will induce a voltage in the coil which opposes the applied voltage. Okay. Now we have seen that this magnetizing current will be lagging the applied voltage by 90 degrees ideally, and the magnitude of this magnetizing current would depend upon the permeability of the core. Okay. So we have seen that the AC magnetization is different than DC magnetization. In DC magnetization, all this back EMF is not present, and the current is purely decided by the circuit element, namely the voltage, DC voltage at the winding terminals and the inherent resistance in the winding. Okay. So we have seen this main difference in DC and AC. Now next we went on to say that there is another phenomenon that takes place whenever the flux is going through a cycle. We notice that we observe a phenomenon called a magnetic hysteresis. So the core goes through a magnetic hysteresis phenomenon or a hysteresis loop, with the thing that the energy is taken at each cycle from the source, but that much energy is not totally returned to the source. It is retained in each cycle, which will be that energy that is retained will be proportional to the area of the hysteresis loop and the maximum flux density. Okay, and we call this energy that is lost in this process per second is the power, and that power is called the hysteresis loss. And we got an expression for the hysteresis loss in the last class. Okay. Let us say pH, we say is proportional to some constant, let us say C1, and we said it is proportional to the frequency, because higher the frequency, higher the loss. That is obvious, because it is frequency, that is the power per second. And we said this is proportional to also the B max to the power of n, where we called n as a Steinmetz's constant, named after. So this was what we learned in the last class, and n we said is typically in a range 1.6 to 1.6 to 2.5. Okay. So we find that hysteresis loss in a core has this relation. It is proportional to maximum flux density. That means to what extent maximum flux density in the core it can go. If we increase the maximum flux density, obviously the hysteresis loss will also be altered. So you must know it is very much depend upon this, and as well as the frequency, and of course C1 is a constant which will depend upon the property of the material, okay, and the area of the hysteresis loop. So in order to, how do you reduce hysteresis loop, hysteresis loss? Okay, so we must know how to reduce this loss, which is, how do you do that? See, you have to operate at a given flux density, because the maximum flux density depends upon the maximum flux in the core, and maximum flux in the core depends upon the applied voltage. Since you normally want to apply a rated voltage, the cores normally operate at a rated flux. Okay, most of the cores you would like to operate at a rated flux density and rated flux. Therefore, you would not like to alter normally this, and you are also would like to operate at a nominal frequency. Okay, that is also fixed. Okay, yes.
We cannot alter. We cannot alter the flux, but we can increase the area so that our flux remains the same while a B comes down.
Yeah, but then what is it a very economical sense? That means you, in a given core, it can operate at certain given flux density. So typically maybe 0.8 to 1 Tesla maximum flux density, which is operated 1.2 Tesla. So why do you want to underutilize the core? So again, that is not, it doesn't make an engineering sense. Therefore, we would like to choose material which will have a minimum hysteresis loop. Minimum hysteresis loop. Okay, that means you must have a very good material, basically soft magnetic materials. Okay, so we would like to do it like this. Okay, now this is one phenomenon. Let us look at another phenomena, which is like this. We have seen a core. Let us take a core as we did last time. So this has the third dimension also. Okay. So let's say you are just going into the perpendicular to the board also. So let us say this is n turns. Okay. Now this, we have seen that it is applied with a voltage which is varying with time. Okay. Now let us take a some cross section like this. So what we are actually seeing is some type of a cross section of the same thing. I just taken a small block of this, in which the it's going like this and maybe coming out like this. Okay, means, and of course it goes through several turns. Okay. Now, and your flux is, the changing flux is going like this. Okay. So obviously you have a flux which is changing with time. Okay. when the flux changes with time in the core, there is, after all, core is also an electrically conducting material. Then what will happen? When there is a change of flux in the core, what do you expect? So there will be voltages induced in the core. Okay? So we note that due to change of flux in the core, voltages are induced in the core. In what direction? To follow the which law? Lenz's law. As per, in a direction to follow Lenz's law. Okay? That means when the flux is increasing, it should create a current in a direction to decrease that flux. Okay? So what will happen? Which direction will it be? If the current is induced this way, then it will create a flux in the upward direction. So it will be in this way. Okay? So let us say you will have a flux currents and voltages induced this way. Okay? To oppose this flux. Okay? In fact, you will notice that the induced currents will be a mirror reflection of the injected currents. So you are putting a current in the winding like this. So this works like a short circuited secondary in a way. Okay? So the direction of the currents in the core, wherever, will be that which will be opposing the change of flux. Okay? So whenever there is, if you say it is flux is increasing, that means it will cause in this direction to decrease this flux. Okay? So since what we are trying to say is, since the core is conducting, see, core is electrically conducting. Because it is a conducting material, silicon steel is a conducting material normally. So currents are induced. Induced to oppose change of flux. Okay? They oppose change of flux. It's very simple. Therefore, while your induced currents are like this, while your injected currents are like this, induced currents will be in the other way around. Because that's how it is going like this. Okay? Now these currents are called eddy currents. Okay? Okay. Now, throughout the core you will find such currents at any cross section. If you take any cross section, they will be induced in such a way. For example, if it is here, it will be inducing in this direction. Okay. So if it is this way here, so it will be here this way, so that it is opposes the flux. Okay. And here also, if you cut it here, they will also produce certain like this, okay, which will again be in which direction? So it will be like this. Yes, other way around. Okay. Huh? Because the flux is going down, so it will be like this. Okay. Now, if it is going this way, so it is this way. Okay. Because the flux is now going down. Okay. So you will notice that it's almost the same sort of a patterns you have to see. Even here, it is this way, so that the flux when it is going, and in the other side it will be opposite of this. That means the eddy current direction here, if you just cut it here and look from the top, and here will be opposite way. Okay, and same thing here to here, because the flux direction has changed. If the flux is increasing here in this direction, okay, flux is increasing here in this direction. Okay. Okay. Now these currents obviously are decided by the voltage is induced because of the flux, and the currents are induced because of the conductivity of the core material. Okay, and these currents, what will be its impact? So it will again, these currents cause losses, which in turn cause losses, and these losses are called the eddy current losses. These are called eddy current losses. Okay, that will again be taking place in the core, similar to hysteresis loss. Okay. Now, how can these be reduced? Can you reduce them?
Yes, sir.
Yeah, by laminations. So can be reduced by using laminated core. They can be reduced by using laminations in making the core. So whenever you see an electromagnetic device which carries AC, you will invariably see that the core are made up of laminations. It is not a solid iron, but a laminated pieces are stacked together. So what you do is, instead of this, instead of making a solid one, so you will have laminations like this. So you cut it, they are fixed like this. Okay. So that means they will all be, let's say each one is a sort of a, so these are, let's say, laminations. The core, if it is solid core, then there will be more eddy current loss. Supposing, let us say what will happen if you make it through laminations and stack them together. Okay, you make a thin sheets, stack them together to form the respective length. Then instead of this, there is no path here, and you will also make sure that between the two, these are all insulated. I mean, that means laminations are insulated. That means they are coated with insulating material, so that even when you stack, it doesn't form an electrical short circuit. Therefore, you would expect, instead of currents going like this, you would expect current just goes like this. Okay. Okay. So this will give a sort of each one a longer length. It is, after all, it's V square by R of the length. So if you are increasing the resistance to that, in this process you are increasing the resistance to the current path. Okay. So basically you are increasing this because you are increasing the length of the current path.
Sir, how are we increasing the length of the path, sir?
Because after all, this whole voltage, flux is now, after all, each lamination will be cutting less flux for the same. You have these. You will see they are all. You are just making a cut instead. This is almost like a dead short circuit of a big core. Okay. So here, each of the, because the flux also is reduced to each of the sheets in a way. Okay. And the flux density, then this is one resistance path. Compared to this resistance, to several resistances like this, so the currents, after all, if you have a thick sheet and make it smaller sheets, obviously currents in each one of them will be smaller. Okay. Pardon?
The resistance are also decreasing. The flux is also decreasing.
No. For if you increase the for the same voltage, you see, if you have this path, now you are making it, your resistance path you have increased for the same voltage, overall voltage. Okay.
So when we cut the sheet, the path will decrease, sir.
Path will
Decrease, sir, not increase.
no. See, some of the current, see, you look at the currents which will go into each of the sheets. That magnitude of current that will be run, because your whole of this whole path is cut now. Okay. So if you look at, after all, even if it's the same this thing, so the current that will be induced in each of the sheets will be considerably smaller. Okay. Compared to what it would be if you have a dead short circuit. It is a common sense. If you have a thick bar, a thick sheet, if you cut it, okay, into smaller one, obviously there will be overall increased resistance to this path. Okay. Now, if you do this,
reduces the core action of that core thing.
pardon?
So doesn't lamination reduces the core action, so the linkage.
Lamination to some extent, yes, it reduces the flux path also. But that is much, because you stack it together, magnetically you don't want to change much, electrically you want to have a considerable increase. You have insulating the two sheets. Okay, several sheets are being insulated. In fact, very, very thin sheets. So you will observe that the currents are almost negligible, considerably reduced, instead of having all of them together like a thick conductor. So it is like saying that, okay, if this is the eddy current which will be flowing, if there is a voltage induced, what you are saying, you are just cutting it into different sheets, so you will see there are very, very small currents, okay, which will go through, you are cutting it electrically. So you are almost insulating it for electrical purposes. Okay. Okay. Now, this eddy current loss depends upon what factors now? Can you tell me? Huh? Material property, then huh? The flux, then frequency. Okay. So similar to hysteresis, it depends upon the frequency of operation, it depends upon the operating flux density, okay, and it depends upon the material properties. So a similar expression for eddy current loss will be like this. PE, that is eddy current loss, is some constant, again some C2 into, it is proportional to F square because it is I square R is proportional to V square and so on, and is also proportional to B max square because it's basically V square by R, because V is the voltage which is induced because of the flux, okay, and then it is also proportional to the T square, where T is the thickness of the sheet. For each of the laminations thickness, you will have this, okay. So this loss is also prevalent in AC magnetization, not in DC magnetization, okay. You see another factor here, okay, and both hysteresis and eddy current losses are prevalent in what part of the magnetic circuit? It is in the core part or iron part. So the total is called the iron loss or core loss, is, let us say, PC is PH plus PE, the sum of these two. Sum of the hysteresis loss eddy current is normally termed as iron loss because it is in iron, or a core loss, it is in core, okay. And you will also notice that one is proportional to F, another is proportional to F square. So you will see this is some constant times F plus another constant times F square, provided your B max and F are fixed, okay. For constant B max. For a given core, supposing you are operating at a constant B max, you can say this is can be written as K1F plus K2F square, okay. Or just one second, or you can say PC by F will be K1 plus K2F, okay. So if you plot, if you can calculate the core loss at different frequencies, what will it look like? So it will be a straight line like this. So this will be K1, sorry, this will be K1 and the slope K2. So you will find that this way, if you can calculate or measure the core loss at different frequencies, you can separate them also. So this way, after finding K1 and K2, after finding K1 and K2, we can separate PH and PE. So if you want to know what is the difference, you will also have PH plus PE, okay. So you can measure the loss for any given core. You can measure the loss at different frequencies and get this division done. Okay. Right. Let's come to one important next point. So we know that there are two of these losses are there. Their iron losses are available. Now, if somebody wants to design an electromagnetic structure, he should have a mechanism to know how much is the iron losses. So you need some type of a design data to be given by the manufacturers of the materials. Okay. So normally, a design data is given by core manufacturers not core material manufacturers, because core you are making, they only provide you the silicon sheet steel. Okay, most of the companies, this is also a material science area where you must like to have a very good material. What do you mean a very good material? It must have a very good magnetic properties. What is very good? Yeah. It must have very high core loss. So it must have a minimum core loss per unit volume, and it must draw very small current. Okay. So design data is given by core material manufacturers to find PC. Okay. Now what they give, okay, what they give is for given Bmax, they will tell you the core loss per unit weight or volume, or maybe that means it may be watts per kg. Watts per kg of core loss it will give you. So it may be somewhere. So this is, let us say PC. Okay, that is the power density. That is how much power loss density. But I have given you in one of the handouts one of the material properties. So therefore, what will you do to calculate the core loss? You know the operating flux density. So you find out the, see, for the given flux density, you find out the core loss per unit volume weight. Then you must know the weight of the core and say this is the core loss, total core loss. Okay, and these are one of the design curves which would be useful for any of the designers of electromagnetic systems. Okay. Okay. So we have seen that in AC magnetization there is the magnetizing current drawn depend upon the flux, which in turn depends upon the voltage. Second one we know hysteresis loss, and third one we know about the eddy current loss. So these are what happens in AC magnetization. There is one more phenomena which happens. Let us see it like this. We have seen this BH loop, and what is the x-axis will be? Make it little symmetrical. Okay. what is the x-axis will be h, and also it will also tells you the I, and this will be the B, and let us say it also operates the flux, or it is also has something to do with the voltage, okay, because the flux decides the voltage, okay. Now if the flux is, if your applied voltage is sinusoidal, then what will be the flux variation? So that should also be sinusoidal, except that it will have a phase lag of 90 degrees. Okay. So let us draw this, let us say you have the maximum flux this is flux which will go from phi max on the positive side to minus phi max. Okay. I mean, let's assume it's sinusoidal. Now, for each of these, for each point in phi, you will have another point of I. Okay. So, whenever there is a, each of the flux will have a corresponding I. Okay. So, if you really take a BH loop and from sinusoidal you do a graphical plotting, you will notice, interestingly, after all, it has to follow in the, I will be varying from plus I max to minus I max, isn't it? So you may notice that this will follow a pattern like this. Okay. So this will not be sinusoidal. The current here, this is current. So if you actually look at the waveform of a current in an AC magnetic circuit, okay, when it is like this, because of course this will be I max, maximum value, this will be minus I max, corresponding to this, but intermediate points, if you take, they will have a different, it will, because the loop is not linear. When will this be sinusoidal? So when instead of this you have a straight line like this, only then, sorry, if it is a straight line, then each one will have a linear relation. Okay. Since this is non-linear, so you will find the next phenomena is okay.
So for each phi, each plug we should have 2 points corresponding to the 2 sides of the. But we are having only 1 point on this.
Where? No, you follow. What I am saying is, supposing if for each one you have to plot. No, this is very rough. Because of the, but you can try. Supposing this is flux is 0, you will have an I. Okay, so you must take the corresponding flux 0. Supposing you say the flux is 0, it may be even here. Okay, suppose you start from here. Okay, then you are increasing the flux to phi max. Okay, then for each one you must plot here. Okay, even when you are going from phi max to 0, you have to follow this path. Okay, and follow and corresponding currents you must plot. Okay. I mean, this has to be done a little more systematically. Okay. So what we are trying to say is, as the flux changes from 0 to phi max to 0, 0 to minus phi max, from minus phi max to 0, you are operating a loop like this. Okay. And for each of the flux, there is a current. So you will find the next phenomenon is that current is not sinusoidal. Normally, it has third harmonics. Yes.
So which current is this? Is this the electric current that is applied or the magnetic current that is flowing through the circuit?
Both are same. See, after all, there are no two currents. I have only one winding. It is having drawing a current. Okay, that current is going to magnetize the core. Okay, and because that magnetization is decided by the voltage applied. So that current that is drawn from the supply will be non-sinusoidal.
But then the current would be lagging.
But voltage is sinusoidal, current is not sinusoidal. Okay? So this is what you will observe.
Still 90 degrees.
Yeah, 90 degree shift will be there. 90 degree shift will be for the fundamental.
Sir, but how can we have a shift when they are not sinusoidal even? What do you mean by a shift there?
Fundamentally shifted by 90 degrees. Okay? Yeah. See, initially we assumed it is a sinusoidal variation of voltage and current. But in actual practice, because of the non-linearity, over and above that fundamental, there is a third harmonic component coming. Okay? That fundamental is in ideal situation where the magnetizing current is expected to be sinusoidal. Okay? So this is what you will observe. Maybe I am trying to get some experiments organized to show you how they form a non-sinus. You can see the waveforms maybe in next class or whatever. Okay. So these are the different phenomena that you will observe. So let us sum up what are the AC magnetization. To sum up the following points, number one is the flux, it is the voltage causes the flux which causes the current, which is not same as DC magnetization. In AC magnetization, it is the voltage which causes the flux which causes the current. Okay? And number two is ideally I lags V by 90 degrees, and I depends on the required flux and the reluctance of the path. And we see in AC magnetization there is the phenomenon of hysteresis. We also see in AC magnetization phenomena of eddy currents. So you will find these two are the one which results in losses in the core, which is there in, these are only in AC. All these phenomena only in AC and not in DC magnetization. Okay. Then we also found out that magnetizing current is non-sinusoidal. Even if the voltage is sinusoidal. So these are the few of these phenomena that you observe. Okay.
So
Yeah.
in a DC case, I plot the various values of phi with respect to I.
Yeah.
Would I get a straight line?
In the case of a
DC circuit.
phi versus psi depends upon the material. It will slightly in the linear region and become saturated later. Okay. Okay. Now About the electromagnetic phenomenon, the only thing that is remaining is the force. What is the force operating on a magnetic field? The force density at any point is, what is the field equations that you know? Q into okay, this is the force at any point in the circuit. You have the, now in most of the circuit that we are dealing with, we have seen that electric field is considerably smaller, okay, in most of the conductors, okay. Therefore we can neglect E and we can write that the force is Q into V cross B, because we have one component of current which is due to the movement of charges. Okay, V is the velocity and this is the movement of charges. Okay, so we can get a simple expression for the force by writing that this force is our force density, that is the rho dV into V cross B, where rho is the charge density. In any given volume, the rho is the charge density. We have rho dV into, or we can say rho V into dV cross B, or if you have the charge density into dV, so you can write this as J d. Pardon? Okay. This is the volume. Because the charge density into velocity, they are moving, so that will have a dimension of a current density J, and I will complete this aspect today by writing
This is force density or force?
which one? Force in a, no. How, you see, for force you need to multiply by the, because you have to integrate for the whole body, okay. At any point, this is the, yeah, okay, sorry. But it is for the given charge, that means it is for the given charge and for the given current density. So in fact you will have a expression for force will be given by IdL cross B. If you have a small element dl, okay, and you have the, so standard expression for force for this, okay. So these are some of the phenomenon, electromagnetic phenomenon, which we have I mean, these will be we will be using in subsequent lectures. How we do it? Okay. Okay. I would. I